السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله وعلى آله وصحبه ومن والاه ومن استنى بسنته واهتدى بهداه. نلتقي اليوم عبر منصة جسر للتدريب التابعة للجمعية السعودية للعلوم الرياضية في محاضرة علمية بعنوان Data in Mathematics Courses Addressing Global Challenge تقدمها البروفيسور ديب، وسوف يدير هذا اللقاء الدكتور فهد الشمري، فليتفضل. تفضل دكتور فهد.
Assalamu alaikum. Hello everyone and welcome. On behalf of SAMS and the organizing committee, it gives me a great pleasure and honor to introduce today's extra special talk by an extra special person, Professor Deborah Hughes Hallett. Deb is a professor of mathematics and math education, a Cambridge graduate. She works for two well-respected institutions, Harvard University and University of Arizona. Deb is a very active mathematician in improving teaching of mathematics and promoting international collaboration between mathematicians. Among her activities and work, she co-organized Harvard's Calculus Consortium for Higher Education. She started a foundation to promote innovative curriculum and pedagogy, served in various committees for the National Academy of Sciences, organized 3 international conferences on the teaching of mathematics. She is the author or co-author of 7 books, which were translated to several languages. Her work was recognized by prizes from Harvard University, University of Arizona, Association for Women in Mathematics, and the Mathematical Association of America. Today, Deb is going to shed some light on some areas where math is very useful. We all know that it is actually a fact, mathematics is very useful. And I guess for most of us, we probably don't care for that as a motivation for us to do math. But the question is, do our students know this? It is actually our task to use every chance we get to make sure they do. This is part of keeping them interested and motivated to continue learning mathematics. Deb will talk about that and much more, and she will be very specific. She will discuss the introduction of discrete data into calculus, the benefits and the challenges. She's going to do this for the next 45 minutes or so. Then we'll have some time for questions and comments. Deb, the floor is all yours.
Thank you very much, Fahd. And let me start by sharing my screen and then set the stage for the talk. Okay. Let me start in exactly as Fahd said, not talking directly about mathematics, but about its importance in the world. Fahd gave a very good explanation that many of us got into mathematics because we enjoyed it, we saw its power, and we felt that it was an important subject to study. Our students are more skeptical. Perhaps the general public is more skeptical. I support your point exactly, Fahd, we need to take every opportunity to emphasize for our students the importance of mathematics. I'm going to take a particular approach of looking at some particular global problems which I believe are problems in the US, but also in Saudi, and talk about how we as mathematicians might think about including these issues in our courses at the university, also in high school. To make it clear, I was trained probably exactly like many of you, only as a mathematician. My knowledge of these areas is just by being an interested person. It's something that we all can do, and I would make the case that we all should do. Okay. Let me look at this now from the specifics. There are several global challenges that the world is facing at the moment. I'm picking two of them. In your own work, you could pick others. It would be fine. I'm going to talk about the recent or current pandemic, which has affected your life, my life, and all our students' lives more than we wanted. And it may not be the last one. In fact, it probably won't be the last one. The other issue that I'm going to talk about is climate change, and in particular, the impact of sea level rise. Now, I know that most of you are probably sitting, many of you are sitting in Riyadh, where it's high and sea level rise may not affect you directly, but your country, like many others, will be affected by climate change. Even if you personally are not flooded, your economy is going to see the impact of climate change. And I think that we and our students should think about how this works. And I believe as mathematicians, even those like me, trained only as mathematicians, have something to add, something important to add, something important both to our students and also to our profession. We not only have to convince our students that mathematics is useful, we also sometimes, perhaps often, have to convince our countries that the field is useful. Looking now specifically at our students' point of view, and I'm going to talk partly from the US and partly with some other examples. In the US, the most common job openings that people have trouble filling are healthcare. As the population ages, more people are needed in hospitals and nursing homes, and in data science. Data science is a new field. I am not a data scientist, but I believe that introducing our students to some of the ideas of data science is enormously important. Many of them are potentially going to go on and be quite successful in the fields of data science. To open the world to our students, I believe that they need to see more than just classical mathematics. Although I was brought up like you on classical mathematics, and I love it. But to be part of the current world, the world that your students and my students are going to be living in, they need to understand data. Data has become common and accessible now in ways that it was not when we were growing up. I think we have to change. And I want to give an example of changes that I think can be made. And in fact, I have been making in some of my courses. You can probably think of other possibly better examples. But my point is to set students off into a successful position in the 21st century. They need to be able to find data, to analyze data, and to be comfortable with data. You might say, well, they learn that in other courses. Probably not. In most cases, people assume that students kind of know how to deal with data already. I think this is not true. So I think we should play our part. Looking at data, so this is from the US, but I believe it's true worldwide. Getting a position as a data scientist is important. There are lots of openings. There is as yet not very many clear trainings for data scientists. So many of our students have an opportunity to expand into this area. And in fact, the rewards are good. And the problems, if you don't do it, are also noticeable. So here are quotes from substantial people in the US over the last few years. You will understand data is the new oil. Without big data, you are blind and deaf in the middle of a big highway. You don't know what's going on if you can't read the data. We want our professionals, whether they're civil servants, whether they're officials, we want them to understand the data. I'm making the case that that starts with us, with mathematics. Data will speak if you're willing to listen. It's true, you can learn a lot from data. I'm assuming that you, like me, did not grow up knowing about data or about pandemics or about climate change. But as academics, I think we like learning new things. And this is our time. Let me say something about the specifics of it. This is from the mathematical point of view. At the moment, I'm proposing only that we include data in standard courses. Of course, it's completely possible to do separate new courses. That's a different matter. But it's useful, I believe, to include data in many standard courses. It has some challenges, some mathematical challenges. One of which is we are used to a field, and Farhad alluded to this, we're used to a field in which things are continuous, they're precise, they're neat. For many of us, that was why we went into the subject. We like the precision. I do too. Data is discrete and it's messy. It's messy because random world events affect the data. It's harder to deal with, but that's part of it. I think our students need to know this. It emphasizes, the use of data emphasizes some different mathematical questions. The role of parameters. When you're fitting a model, you usually pick the style of the model first and then adjust the parameters to fit the context. The role of parameters is in fact extremely important. Making projections over the last year and a half, I'm sure that you, like us in the US, have watched the COVID numbers, the infections, the positivity rate, the deaths, trying to understand what is the trend. Do we need a lockdown? Are things going to get better? What effect have vaccinations had if they're accessible? Making projections is extremely important. In climate change, that's enormously important because the bad effects of climate change, some of which are being felt now, are mostly expected to be felt in the future and will potentially have an enormous effect. But we have to believe the projections in order to plan how to adapt. And the planning cannot wait, I think, until the disaster strikes. So understanding projections and understanding what they tell you and also what uncertainty means and how to deal with it is a very important part of thinking about data and models. What tools do we use? There are many. I've been using very simple tools, mostly a spreadsheet or a calculator, and looking at scatter plots. You don't need a lot of powerful mathematics. You certainly can use it. It's great to use it, but you don't have to use it. Even quite regular tools, particularly spreadsheets, can be enormously useful. You may not think of part of mathematics as having people use spreadsheets, but they're useful. And I think it's probably worth many students getting more comfortable with them. How does it fit into standard courses? Here's a list. So the COVID-19 data particularly fits into pre-calculus. This is families of functions, thinking about linear and exponential growth, logarithms, parameters. It also fits into differentiation, integration, differential equation, and statistics. There are lots of different places you can put things. I'm going to give examples of problems that I have made and used in courses that I've been doing or talks that I've been giving over the last year. Climate change fits in many of the same places. So I'm looking at this in terms of pre-calculus and calculus and statistics, but it's certainly possible to put it in many different places. Okay. So what I'm suggesting is that we think about global challenges. I'm thinking about COVID-19 and climate change. You can think about something else and include data that's real data in those courses. Will the students know where to find it? Not necessarily. We can help. We can get certain pieces of data. Once the students realize what an amazing collection of data there is out there on the web, ready to be used, it's an important feeling. It's like having access hundreds of years ago to a library. It's a source of information that's extremely rich, extremely powerful, and extremely relevant to this century. Let's look at some specific examples. For COVID-19, what do we want our students to know? So here are my answers to these questions. You may have different answers. Unfortunately, I think that COVID-19 is not the last pandemic that we're going to see. As the world becomes more global, pandemics can find their way around the world more easily. And I think that we should think of this pandemic as one of perhaps others. Now, Possibly I'm being too gloomy, but possibly I'm not. What do students need to know? They need to look at the data that's being collected. I'm sure that you're collecting data of your own. I've been using the Johns Hopkins collection because it's reliable, regularly updated, and I'll show you the link from which it comes. We've put it onto a web page to make it easier for mathematicians to download and use. It doesn't have to be that source of data. We've just found it reliable and easy to deal with. We need to know, our students need to know how the projections are made and to be able to deal with the uncertainty involved. Any projection, no matter how well made, no matter how carefully thought through, is going to have some uncertainty. They need to know how to think about what this tells the government, the officials, about policy. I'm going to show you a bit about different graphical representations. That's very much the first bullet, and about finding the models, and that's mostly the second and third bullets. So here's just an introduction to each of all of the COVID examples. There are two basic ways of looking at the spread. You can look at what we have called P of T, which is the total number of cases confirmed in some region. This one is Switzerland, up to and including day T. N of T in our notation is the newly confirmed cases on day T in that same region. And for us, T is in days. Now, the P of T and the N of T are our notation. You can use different notations, but fundamentally, these two functions, these two variables, are what the websites are reporting. And having taught this last semester to college students in the biology, thinking about how these graphs work and how these functions work is not obvious to students, and I think is important. In particular, these two are looking at what happened in Switzerland in spring 2020. So it's a year ago. Questions you might ask. So there's a math questions. Which graph is P and which is N? You might say, well, that's quite easy. Make sure you ask the students before you decide how easy or hard it is, because mine did not find this particularly easy. They did after they thought about it and after we talked about it. But it wasn't initially obvious to them that because of the way they're defined, P cannot decrease, N can decrease. So the upper graph has to be N and the lower graph has to be P. You also notice as a mathematician that the N graph is very jumpy. It bumps up and down because of all kinds of things which have little to do with math, like when people record cases, when there's an outbreak, and so on. Understanding how the real world interacts with these cases, I think, is important. It's also worth, I think, pointing out or getting people to understand, if you're doing calculus, that N, which is the change in P over the change in T, where the change in T is 1, is approximately the derivative of P. So the upper graph is roughly the slope function of the second graph. This is true anywhere in the world. It's not as neat as the problems in a calculus book, but it is, I think, important. Here is a problem that I actually gave last semester. You're given two P graphs and two N graphs, and each of the two belong to one country. So you're asked to identify which are the P's and which are the N's. This is actually on my final exam. And you can see here that the two P's have to be 2 and 3. And what are the corresponding N's? Well, thinking about the slope interpretation, you can see that the times that there were big peaks in N, a huge number of new cases, the P graph went up steeply. Consequently, the bottom right, 4, has this huge peak at about 320, and that corresponds to this vertical jump up here. This graph, which has 2 peaks, corresponds to that increase and that increase. This kind of graphical differentiation, which is what this is, I think is important. These two graphs happen to be Moldova and Ireland, but that's not part of the question. So I've used this to teach how the derivative function relates to the original function. Arizona, where Farhad and I have both spent time. Okay. How do you find the model that is being used? So this is Arizona last fall. It's a second wave. So Arizona had a huge wave of COVID cases in June, and it had a second wave a lot of the fall. I want you to look at the blue, which is the real data, and the red, which looks exponential. How do we know that is, or whether that is actually exponential? That's what fitting the model means. Let's look at P primed, that's N, in comparison to T. Knowing what you know about exponential functions and that the derivative is also exponential, that looks like it could be exponential too. It's concave up, but it hardly is convincing. It could be other things. What else can we do? A common technique, and those of you who teach differential equations undoubtedly know this, are used to doing this, is to look at P primed over P. In other words, N over P. And although that's quite wobbly, it is approximately a horizontal line. Now, I agree, it's not precisely that at all. This is one of the differences between using data and not. But it is generally in the trend of a horizontal line. The line at 0.03 is roughly where that P primed over P data goes. What does that tell us? It tells us that this data does satisfy the differential equation, which leads to an exponential growth. So the number of cases, the second wave cases in Arizona last fall were growing exponentially. They did so for months. If you think about the human suffering that that represents, it's an important observation. Look at South Africa, a new example. Here, this looks pretty similar to last one, looks sort of exponential. Here is the P primed over P. It looks slightly like, whoops, it looks slightly like there are two lines here, one at 0.3 and one at 0.05. What happened? That enormous drop is the effect of a very severe lockdown. It had a huge effect. Another way of looking at this data which may or may not be familiar to you, is to look at a logarithmic or ratio scale. So the left data is the same data. The right is on a logarithmic scale. Look at the vertical scale and look at the graph. It has a corner. That corner is the lockdown. So we can see the effect of policies, lockdowns, in the data. Now let's move to your country. This is the Saudi data between January of last year and June of this year. The blue is your actual data. The red is a logistic model. And did it fit well? Not perfectly. It stopped fitting as well sometime earlier this year. You probably know far more about this than I. How could your students find this model? Let's look at this. On the left is the same graph. On the right is a graph of P primed, that's N, against P. Looking at the logistic differential equation, we expect P primed against P to be a parabola. So the red graph on the right is a fitted parabola. Does it fit perfectly? No. Does it fit somewhat? Yes. Data science is a very imprecise science in comparison to what we are all used to. What does this tell us? Well, it tells us something important, that if you take the equation P primed equals 0.0001 P squared minus 0.0383 P, which is what you get by fitting the parabola to it in Excel, we discover something that you probably would have wanted to know a year ago, namely when the pandemic might level off. The 383,000 in the denominator of the lower equation is the carrying capacity as predicted by the logistic model. This is something that your students and mine can do in calculus. I'm only using Excel and I'm using the Johns Hopkins data. And what it tells us is initially the cases in Saudi Arabia were growing exponentially, initially at about 3.83%, and they leveled off to a bit less than 400,000. Yes, it's imprecise. Is it useful for the country to know this? Yes, because it tells you something about how many hospital beds you might need, how many doctors you might need. It's important knowledge, and it's knowledge that your students can do even while they're at the beginning at university. You can also do, I'm not going to do this in detail, here's a slightly more detailed example, looking at the Gompertz model, which is a different model. I'm not going to do this because it's a little bit more complicated, but it's something that first year calculus students can certainly do. So I would urge you to think about ways that you can include things that you think are important in calculus courses, things that you think are important outside of mathematics. It's not that it's wrong to talk about what's interesting in mathematics. It's totally a good idea. But to keep students engaged, we need them to know what our subject does for the rest of the world. one of the things I think it does is to help us predict and monitor pandemics. Now let me move to a second example. This is unrelated. I'm just giving two different examples. And you are very encouraged to add your own examples. I'd be very interested to hear from you about what you think is important. So this example is about climate change. And in particular, I'm going to look at sea level rise. There are many other things. The US at the moment is having an enormously hot summer in parts of the Southwest, to the extent that some of the reservoirs are drying out and people don't have water. There are serious forest fires that are partly enabled by the very hot temperatures and the very dry circumstances. So there are many other things that you can look at. They're all important. I picked sea level rise because I think it was interesting. I'm in Boston, which is on the sea, and sea level rise is an issue here. Some of the themes here are very similar in the COVID example. What the data is telling you, understanding what the data is saying is so important. In particular, for sea level rise, the planning to adapt to sea level rise, which you may never have thought you as a mathematician had a role to play in, but I am arguing that we do, by making the subject understandable and important to students who may not end up in mathematics, but who may end up managing cities, doing work where they do have to prepare for sea level rise. Unless they know what's coming, they're not going to do a good job. Many of the same issues, mathematical issues, appear with sea level rise as they do with pandemics. There are projections, and the projections are always uncertain. And the people who would like to do nothing always say, oh, well, the scientists don't know what they mean, and so they are wrong. Any honorable projection has an uncertainty involved in it, often a big uncertainty. We need to have officials, policymakers, our students understand that even though there is uncertainty, it doesn't mean you should do nothing. So I'm focusing on sea level rise, but you are welcome to focus on other things. Here are specific examples. Here I'm going to give all US examples because I don't have the access to the Saudi examples, but I believe that you have them. I'll show you why. So the top two pictures are Miami. Those are not fake photographs, those are real photographs. Miami is on the sea, it's very low, and it's flooding. Not permanently, but the damage is significant. Bottom left is New Jersey. That was after Hurricane Sandy, which did an enormous amount of damage, both to New Jersey and to New York. Bottom right is the Netherlands. They know about flooding for longer than the rest of us have. We probably have something to learn. I'm going to look first at Boston and then at New York. So first of all, to perhaps, I hope, convince you that Saudi does need to think about this, even though in Riyadh, you probably don't. But a number of your coastal cities, which are undoubtedly important economically as well as to the people who live in them, are threatened by sea level rise. What is this graph? This is from an organization right outside Princeton. Its address is here, and I have it in the attributions at the end of the file. They're an organization mostly of Princeton faculty who do very good work looking at the impact of climate change. They have made a series of maps, this is from there, which look at the impact of climate change in different years. The red areas are currently land, but by 2100 are expected to be under the sea. The industries that work in that land, the people that move in that live in that land, are going to need help. They're part of your country. Here's the other side of the country. This is a projection in 2050. So most of your students are going to be alive at this time. What are they going to do? How are they going to prepare for this? You know much better than I what goes on in the economic cities, but my guess is that it's important and that your country's economy will depend on managing this. We can't wait till 2050 to plan. So these maps are open to the public. You can go and look at them. You can make your own. You can zero in on whatever part of the world you'd like. And I did this because I was going to be talking to you. I'm going to look at some of the plans that Boston and New York are making. I'm very interested to hear about what you think is going on in your corner of the world. There undoubtedly are some plans. Since I don't read Arabic, I don't know. So here's Boston. Okay. You might think, oh, that doesn't look too bad, just small spots. I want to zero in on this part of Boston. Why? Because I live there, I know what this is. This area, particularly on the left, is the commercial and financial hub of the city. Boston is a big city. It has an important economy. And this piece of it that's all red is deeply threatened by sea level rise. This is the place where people go shopping. It's where the banks are. It's full of high rises. This is not a place you want to have flooded. It's going to be flooded. There is another group, and again, you can look at your own links and so on. There is an organization at Yale that's making quite good papers about what's going on in the US. I'm sure there are things going on in Saudi, but I don't know what they are. So this is Boston in a particular flood. The projections, these are from Yale, are by 2070, some neighborhoods, those are including the ones, the financial district, are going to flood monthly. That's rather often, resulting in $1.4 billion in annual losses. That's a lot of money. What are we going to do about it? We can't wait till 2070 to do something. I personally would say that we can't wait for the politicians, for the officials to take action. We need our students and ourselves to know what the threats are and what possible action might be taken. I'm going to simplify the problem enormously because I'm thinking of ways that I can teach this to regular students. There are professionals who do it in all its real complexity. but I want my students to understand at least the big issues that are involved, and at least some of the trade-offs that are involved. So my question to my students is, how much should Boston be willing to spend in 2020, so I did this last year, to avoid one of the 1.4 billion costs? Now, clearly the more you spend, the better. But once you talk about spending money, somebody is going to say, where does it come from? And you're going to need to say, if we don't spend this money, the amount we will have to pay later is much, much larger. So let's imagine this is simplified. It's simplified enormously, but it's still real. How much should we spend today to avoid one of those 1.4 billion costs? Let's imagine that the P dollars get spent on building a wall. So to meet the 1.4 billion payment, here comes the math. One way of looking at this, and your economist colleagues, your finance colleagues will undoubtedly do this all the time, is to look at, supposing we want to invest P dollars today to grow into 1.4 billion in the future. In the US, I'm creating a discount rate, which I made 1%, which gives us 849 million. Okay. Now, do I know the discount rate? No, we never do. It's one of the many things we have to estimate. But I would like us and our students to know how to think about estimating the discount rate and calculating the 849 million, which is the present value of the 14,000 million, which is the future value. This involves mathematics that we generally do. It's exponential growth and decay, but it's applied to how you fund a project. So I'm suggesting that we include, whenever we teach exponential growth and decay, these kind of examples. And to keep it real, I also found Boston's operating budget. The capital budget is about 3 billion for the next 5 years. Okay. Presumably you can find similar budgets in your communities. But I believe that your West Coast and your East Coast may need some expenditures to save them from looking like the picture at the top right, or worse. If you're teaching Calculus 2, as you do this over several years, it's either geometric series or integrals. So the picture on the right is in fact the financial commercial district that is going to be flooded once a month in about 50 years' time. Now, you may not be alive in 50 years, and I may not be alive in 50 years, and undoubtedly we won't be, but many of our students will. And if the funding isn't, if the preparations aren't made now, this will flood. There's a human side to this, which is, even if you go for flooding, the disruption is awful. So present value calculations, I think, are an important part of it. Let me give one more example, which is New York. What kind of things might you do with that present value? Well, if you're talking about flooding, you're going to build either a flood wall or on the left, lower left, or a levee on the right. Okay. Or your engineers may have other solutions, but these are the two that are mostly being thought about in the US at the moment. The costs given here come from a Boston City paper. Let's look at this example. So this is a real example. On the right is an aerial view of a regional hospital. This is actually inland. It's in upstate New York, but it's near a big river, and the river floods partly because of climate change. This picture shows 2006 when the river flooded badly. And you can see probably that the water is going into the hospital. On the left, that is the hospital in 2006. It flooded with 16 to 20 inches of water with sewage in it. All the patients, think of the grandmothers, think of the children, think of the mothers in labor. They all had to be taken out and taken somewhere else because the hospital was not usable. There was $20 million worth of damage. They decided in Binghamton, that's the city, no more. And in 2010, they built flood walls to keep the flood water back. I'm suggesting more Excel, more exponential growth and decay, that our students learn how to make spreadsheets. This is one that I made. It's not what they actually used, where we're looking at the different years, the damage or the costs, and the benefits. Benefits are lack of flood damage. And think about how to do costs and benefits for a project like the Lourdes Hospital wall. It's something that the students can do. They can see the effect of different assumptions about discount rates and expenditures. And they can see how to plan for the future. This is the last slide. In 2011, so the year after the flood wall was built, there was another flood. It was equally huge. But this picture shows, this is the flood wall. Those red arrows are showing the water coming right up to the flood wall. But they had built it high enough that it didn't go over the top. This is the entrance to the hospital. The hospital was still working. No patients were evacuated. No grandmothers had to be suddenly moved. No mothers in labor had to go somewhere else. This flood wall saved the hospital. And I want to suggest that our students would have great passion and interest in learning how to cost such a building's endeavor, and how to think about preparing the future that they will, I believe, see on your West Coast and your East Coast in this this century. Okay. Let me end here and say thank you very much. Attached are the web pages I was using. These are for the COVID, and here are the sites I was using for the climate change. So let me stop here and say thank you very, very much. And I would be delighted to hear from you and work with you if you decide to take any of this on. Thank you.
Thank you so much, Deb.
I will stop sharing, but if
I'm sure I'm not going to be the first who says thank God for mathematics. Mathematics certainly save lives. It helps us have a safer future when used carefully, make informed decisions. Let's see, anybody with any comments or questions.
I'm reading the chat. One says, can we have a translation? That's up to all of you. You're welcome to translate. I can't. But I would be very interested to have you translated if you'd like. Yes.
Yes, we could do that. I guess the entire talk has been recorded, and I think we're going to discuss with our colleagues to do something about a translation, have it hopefully ready as soon as possible and posted on the website, SAMS.
I would be very interested if any of you can find similar work with climate change that's being done in some of your coastal cities. I assume that you that work is being done, and I'd be interested to know what it is. There's yes, okay. There are several questions in the chat. Do you want me to answer any particular one, Fahad, or shall I just answer any of them?
Just up to you.
So the question is,
whatever question is clear for you, go ahead.
So the mathematical tools that I was using are mostly quite simple. They're some calculus and looking at data from the web and using, in most cases, exponentials. So exponentials functions, I think, are good. So I think in answer to the person who asked what questions, what are the steps being taken to build a mathematical model, find something that you and your students are really interested in. I think the student interest is extremely important here. And you know the national interest better than I do, so much better. Get some data. You know, I don't know what climate change data there is in your country other than I know the flooding pictures. The COVID data is international, so that's easily there. And think about how to make a projection. The examples I was showing were exponential growth, that was Arizona, and the logistic model, that was Saudi Arabia. And there are some other places that are also logistic. So first I would look at what models already exist and think about how to adapt the data from your country or your area of interest to that data. For the climate change, the modeling I was doing was mostly looking at the costs, because this may not be true for you, but in the US, the big issue is getting people to believe that we should pay for this now. Okay. I personally think we should pay for it now. And so I was mostly just doing present value. That was what I showed about Boston. And the Lourdes spreadsheet, which I'm happy to send you, is basically done, the mathematics in it is the same way. The difficulties are for both of them, that when you're projecting 20, 50 years into the future, people are going to make different estimates, and that's necessary. So you want your students, I think, to be comfortable with saying, I believe that future floods are going to be more destructive or less destructive or whatever they think, and make estimates based on that. Somebody had, yes. Anybody had a question? Yes. Dr. Al-Sayed, were you asking a question or did I answer it? Judy, since you're on from Ohio, do you want to say something about your planning, your upcoming Calculus 1 course? So several of my colleagues from the US and different places are welcome to be included. Someone asked also about books. So the applied calculus book that I have written with a lot of other people, I've written a calculus sequence and also an applied calculus sequence. The applied calculus sequence, which we're just redoing, it's not out yet, but it will be sometime soon, includes both the climate change models and the COVID models. So there are a number of interesting things in the US, and I don't know for you, where cities and towns, which mostly have their own budgets, have thought about how to manage climate change. Vancouver, Canada, so on the west coast of Canada, is a big city right on the Pacific, and it's very much endangered by flooding. And the University of British Columbia, which is in Vancouver, had to build a new boathouse. So they included, they decided to build that boathouse floating. They pay for the extra cost of making it floating by renting it out to weddings. This was an unusual business move. So you could get married in Vancouver at the boathouse, which has a wonderful outdoor deck with a view of the mountains. It looks beautiful. And the money to build this is recouped by renting it out for weddings. So you might want to think about what innovative things people are doing in your communities to pay for pieces of climate change. Okay. There are other places in North Carolina where the coastline is very low and they're raising taxes. This is not popular. They're raising taxes to pay for putting more sand on the beaches. I'm not sure this is financially a stable idea, but that's what they're doing. Somebody asked, are the books available on Amazon? The new version of the book, which is the one that is going to come out in the fall, is not yet available on Amazon. It will first be available through the publisher, who is the US publisher, John Wiley, but they undoubtedly have representatives for you. And if you tell me, I can get you sent copies. So let me know if you want me to get copies sent. The paper copies are definitely not out yet. We haven't finished it, but it'll be out by the fall. And I'm very happy to have feedback or to have Saudi examples.
That's nice. Actually, we're going to take some of these questions and see what is happening in these areas for the decision makers, for the planning in our region. Also, I think it would be awesome if we get some of your books also translated into Arabic, if they're not still still available.
You'd be welcome to. When I signed a contract with Wiley, I kept the rights to translate into other languages myself, so I can give it to you happily.
That's awesome. That's very nice.
I would be glad to.
So, any other questions? Any comments? So. Well, in conclusion, thank you so much, Deb, for this wonderful talk. It's been very motivating. And I'm pretty sure we will not forget it for a very long time to come. So thanks a lot, and hopefully we can do it again sometime.
I'm very happy to. I mean, one of the things that I think is very important, and actually one of the good things that has come out of the pandemic, there are some good things. One of the good things that has come out of the pandemic is now we are much more used to meeting virtually, and collaboration with people in different countries is so much easier than it used to be, because we're all used to it. So it's really an honor and a pleasure to be part of your community, and I would love to stay part of it. Thank you very much, Fahad, for organizing this, and Reem for putting it all on. Thank you.
Thank you so much. Thank you.
شكرا لك دكتور فهد الشمري. Thank you very much بروف ديب، وإن شاء الله لنا لقاءات أخرى في منصة جسر. شكرا لجميع الحضور. السلام عليكم.
يعطيكم العافية. شكرا جزيلا أستاذ زهور.
عفوا، شكرا لك.
So as mathematicians, I think that we need to work together, unite across the world to think about what we can do to show students the importance of our subject and the important role that we play in thinking about how to manage some of these global challenges, because mathematics is extremely important. So thank you for having me.
Thank you. Thank you so much, Deb. Have a wonderful day.
And have a wonderful night, since I know for you, it's evening. And for me,
That's true.
it's morning.
That's true.